42,000 years ago, unusual events occurred on Earth. About 42,000 years ago, the Earth experienced a significant historical turning point. Unusual electrical storms and extensive auroras occurred alongside an increase in cosmic radiation. The catastrophic climate changes and mass extinctions were caused by a transient change in the Earth's magnetic field. A planet's magnetic field is one of the most significant determinants of its fate. As with Mars, a lack of magnetic field can render a planet desolate. It can even determine whether a person lives or dies. The Earth's magnetic field shields us from cosmic radiation and solar-emitted charged particles. Consequently, a sudden change in the strength of the magnetic field could inflict havoc on Earth, and a similar event occurred in the recent past. But what precisely occurred 42,000 years ago? How did scientists uncover the change that occurred in the magnetic field in the past? Will a similar event occur soon? Let's examine the origin of the magnetic field on Earth. It is known that most planets in the solar system generate magnetic fields because of the movement of electricity-conducting fluids within them, and the same holds true for our planet. In terms of the inner structure of the Earth, there's a 3,400-kilometer-long region of iron alloys. It comprises a solid interior core with a radius of 1,220 kilometers and a liquid outer core. As the planet rotates, the rolling of molten metal around the planet's iron core generates electricity that produces magnetic field lines. These lines curve from pole to pole around the planet to create the magnetosphere. The magnetic field of the planet functions as a natural protection. It provides protection against hazardous solar radiation. On the side facing the sun, the incessant bombardment of solar wind compresses the magnetic field. Consequently, the field on this side extends to a distance no greater than 10 times the radius of the Earth, whereas it extends further into space on the opposite side, facing away from the sun. The two locations formed an arch. As a result, magnetic field lines converge at the magnetic North Pole and the magnetic South Pole. Although these positions are comparatively stable, the magnetic poles and magnetic fields are not fixed because of the constantly changing forces. The field intensity fluctuates. It becomes weak enough every 200,000 to 300,000 years to completely reverse the polarity. It is believed that this magnetic field reversal occurred between 41,000 and 42,000 years ago. This event is referred to as the cosmic bubble. Our solar system is in the middle of a mostly vacant region of space. This cavity has a particle density at least 10 times lower than the average density of our galaxy's interstellar medium. In addition, it contains a thin group of X-ray emitting plasma with temperatures that can reach 1 million degrees. This cavity is the local sphere, where our sun and thousands of nearby stars reside. However, how did we find this bubble? How did it initially originate? When did the sun penetrate it? First, the local bubble is not spherical, so calling it a bubble is inaccurate. Instead, it appears to have an hourglass shape, narrowest in the galactic plane and expanding above and below it. In addition, the bubble appears to have no end and explodes into the galactic halo in a direction away from the galactic plane. It has a diameter of approximately 1,000 light-years and is enveloped by colder, denser, neutral gas and dust. Several cloudlets of the interstellar medium and cosmic bodies are aligned in sheet-like structures near the bubble's boundary, along with several neighboring stars within this vacuum. Currently, the Sun is enveloped by a cluster of cloudlets known as the local fuzz complex. Then, some passages branch off the local bubble through the surrounding dense gas and lead to the opening of additional cavities. These interconnected cavities and tunnels are comparable to the pores in a typical sponge. Using a combination of optical, radio, and X-ray astronomy, the local bubble was discovered between the 1970s and 1980s. However, for years it was unknown how such a structure initially formed in a typical sponge. As a result, different missions have been undertaken to study the bubble's anatomy over the years. First, the Extreme Ultraviolet Explorer mission, which ran from 1992 to 2001 and investigated hot EUV sources within the bubble, considered it a region of particular interest. Then, in February of 2003, the Cosmic Hot Interstellar Plasma Spectrometer CHIPS, or CHIPSAT, was launched. This mission lasted until 2008 and investigated the heated gas within the local bubble. The most significant achievement in studying this cosmic void occurred in 2019, when researchers published the first 3D depiction of the local bubble based on observations of diffuse interstellar bands. A precise map was drawn with the data published by Gaia. Gaia is an ongoing initiative that seeks to precisely map the position and motion of stars in the Milky Way. The mission may not be as well known as the Hubble Space Telescope or the James Webb Space Telescope, but its data has significantly contributed to our comprehension of the Milky Way. Gas and immature stars within 650 light-years of the Sun are also mapped by Gaia. Largest known galaxy. Astronomers have found the largest known galaxy to date, and it is so large that it'll shatter your cranium. It is a radio galaxy located 3 billion light-years away in the constellation Lynx. This means it takes 3 billion years of this galaxy's 300,000 kilometers per second of light to reach us. This enormous galaxy, designated Alcyoneus, has perplexed astronomers. What is a radio galaxy, though, and does it differ from the galaxy in which we reside? Moreover, how large is it compared to the Milky Way? A century ago, our exploration of galaxies was a fascinating endeavor. We believe that the Milky Way is the only galaxy in the universe. We had images of other galaxies, such as the Andromeda Galaxy. However, astronomers believe they are star systems within the Milky Way. After a century, the number has increased to 2 trillion. In the universe, astronomers have observed a diversity of galaxies: spiral, elliptical, irregular, lenticular, asymmetrical, interacting, and merging galaxies exist. However, this is merely a clear classification based on what we observe with a telescope in the visible region of the electromagnetic spectrum. Objects in our universe emanate energy over a broad range of frequencies, and their luminosity in various portions of the electromagnetic spectrum varies depending on the energy they emit. This means an extremely dim object in the visible spectrum can appear extremely bright in radio or infrared radiation. Alcyoneus is one of the radio galaxies which are extremely bright at radio wavelengths. Now the query is, what distinguishes radio galaxies from others? What additional information do we gain from radio frequency exploration of the sky? Because of the longer wavelengths of radio waves, radio emissions are one of the finest methods for decoding the mysteries of the universe. They can also travel through dense dust clouds, providing unobstructed views of the cosmos that are otherwise invisible in the optical spectrum. There are various emission mechanics by which radio waves are emitted by astrophysical objects. However, the most prevalent emission mechanism is the phenomenon of synchrotron emission, and most radio galaxies emit radio frequencies because of this phenomenon. What exactly is that? Surely you learned about cyclotron radiation in high school physics class. When electrons in a cyclotron with a circular orbit are sped up in a magnetic field, they emit radiation proportional to their cyclotron frequency. As electrons travel at relativistic velocities, synchrotron radiation is merely the relativistic counterpart of cyclotron radiation. As in other galaxies, synchrotron emission is one of the most potent and dominant radio emission mechanisms. Radio galaxies comprise a host galaxy of stars in orbit around a galactic nucleus containing a supermassive black hole. This is accompanied by gigantic jets and lobes emanating from the galaxy's center. These jets and lobes interact with the intergalactic medium and ultimately operate as a synchrotron to speed up electrons that emit radio waves. This is a common occurrence. Even the Milky Way has radio lobes. In some galaxies, however, the radio lobes expand to dimensions of megaparsecs. Consequently, these galaxies are Triton's strange characteristics. Despite its unique characteristics, Triton needs to be more frequently addressed. Many of its characteristics are singular. Consequently, it is among the most fascinating objects in our solar system. Despite being the largest moon of Neptune, it is the planet's most distant neighbor. Because of this, we have only visited it once, briefly in 1989, 30 years ago. How has it changed, and what has it revealed since the last visit? First, discuss Triton's position in the solar system and the local ecosystem. There are 14 known moons of Neptune, including Triton. 7 moons orbit Neptune's ecliptic in circular paths with extremely low eccentricities. After these regular interior moons, Triton is the first irregular moon. The orbits of irregularly orbiting moons are inclined, eccentric, and frequently retrograde. Triton's spherical structure distinguishes it from other spherical moons in the solar system. The planet's orbit is irregular, as Triton orbits anti-clockwise around Neptune. An angle of 130 degrees is formed between Triton's orbit and Neptune's ecliptic. Even though its eccentricity is close to zero, its orbital eccentricity merits consideration. In its orbit, circularity is almost ideal. Other large moons in our solar system orbit their parent planets in the same direction. This shows that Triton was not formed alongside Neptune, but as an object captured by Neptune, specifically a dwarf planet. This moon comprises 99.5% of Neptune's orbital mass, making it the largest of Neptune's 14 moons. What is the proportion of that? Despite being smaller than the Earth's moon, it is the second largest moon on its progenitor planet. Because of its close orbit around Neptune, it appears roughly the same magnitude as our moon in the sky. Despite being the seventh largest moon in the solar system, it is significantly more significant than Pluto. Since Triton once governed this region before Neptune captured it, Pluto may appear to be the Kuiper Belt's king. Because being Neptune's moon, Triton is the largest object in the Kuiper Belt. In 2015, New Horizons flew by Pluto and discovered that Triton and Pluto share a vertically identical composition, supporting the theory that they originated from the same planet. Additionally, 6 additional irregular moons were found beyond Triton, almost certainly objects with unusually eccentric orbits that take years to complete are captured. The Triton's gravity may have perturbed their orbits. Consequently, how was Triton captured? To capture an object, one must sacrifice speed. They could then escape if they had sufficient momentum. According to the most widely accepted theory, Triton was once a member of a binary system, like Pluto and Charon. As Neptune approached, Triton's moon would have been propelled away by Neptune's gravity, causing Triton to lose momentum and orbit Neptune. As previously mentioned, Triton and Pluto share similar qualities. What does that mean precisely? They also contain water ice, carbon dioxide ice, and nitrogen ice. There are multiple levels of regions there. The maximum difference in topography is 1 kilometer. Voyager 2 did, however, observe plateaus, ridges, and icy plains. Although it may startle you, it has very few craters. Consequently, its surface is perpetually renewed, as is Pluto's. Besides the reddish regions, methane reacted with ultraviolet light to produce tholins and organic compounds resembling tar. Organic compounds do not inevitably support life. Life cannot exist on Triton's surface, as the temperature is too low and the sun is too faint to support life. Under Triton's crust, like Titan's surface, is believed to be a stony and metallic interior, giving Triton a relatively high density for a moon of 2 grams per centimeter cubed. This is because the moon is significantly larger than the next largest moon in the solar system. Titan has a greater mass than all of the lesser moons combined in the solar system. Like the subsurface oceans on Europa, Enceladus, and other large moons in our solar system, radioactive decay from the rocky core could heat and fuel convection in a subsurface ocean. Cryovolcanism is a dynamic phenomenon similar to Europa and Enceladus. On Triton, as on Earth, liquid water erupts from the mantle today. The surface is so youthful. The surface of Triton has been actively renewed by the eruption and cooling of liquid water. Young, sparse, and relatively level lava plains surrounded by an intriguing wall have been discovered. The lake of solidified magma is known as Planitia. Also visible is the caldera that formed at the center of the cryovolcanoes. These eruptions brought minerals from the subterranean oceans, possibly even tholins and organic matter, to the surface. If this is the case, the subsurface ocean may contain organic compounds. Life could have formed there, had the conditions been favorable. Additionally, lengthy lines permeate the surface. These faults are most likely caused by tectonic activity or freeze-thaw degradation. Recent eruptions are visible in some Triton images captured by Voyager 2. Up to 150 kilometers long, surface deposits resemble cones or funnels. The mantle may not be accountable for these minor eruptions. During Voyager 2, the spacecraft detected 8-kilometer-tall plumes, believed to result from a significant greenhouse effect within the Moon's ice crust. Assume that Triton's surface is composed of clear ice deposited on opaque deposits such as tholins. The sun's rays penetrate the ice, warming the darker, more absorbent tholins beneath, which are ice pockets. The pressure created by the sublimination of the ice in the air pocket causes the surface above the air pocket to collapse, resulting in an eruption. Besides distributing the dark deposits across the surface, this eruption also transports the dark deposits. Under the polar ice cap on Mars, carbon dioxide ice and dark deposits have been observed. If this is the case, one factor makes this procedure workable. Researchers initially expected that Triton's atmosphere would be denser. However, approximately 80 kilometers above the surface of the Earth, Triton's atmosphere is only 0.014 millibars dense. However, this density varies seasonally, similar to Pluto's. Since Voyager 2 observed Triton's atmosphere becoming denser as the surface warmed, some of the nitrogen ice on the planet's surface has evaporated. Despite this, Triton's atmosphere was still dense enough to sustain weather 8 kilometers above the planet's surface when Voyager 2 passed. As a result, there are clouds visible on Triton in this image. As seen in the image of the plumes, the predominant wind in that region has caused all eruptive deposits to face the same direction. The hazy atmosphere of Triton is believed to be caused by hydrocarbons that have not yet been broken down by sunlight into tholins. Seasonal variations cause the evaporation and refreeze of ice, while cryovolcanism deposits organic compounds continuously. Rich weather and a lively ambiance make Triton an extremely dynamic place. Pluto is the most well-known moon in the Kuiper Belt, but it is a dwarf planet rather than a moon. These factors combine to make it an uncommon moon. The nearest black hole. Astronomers have made a groundbreaking discovery by locating the black hole nearest our solar system. It is part of a binary system with a star similar to the Sun orbiting it. Initially, astronomers believed it to be a typical binary system comprising two celestial objects. However, when they examined the star's properties and how it orbits the black hole, they immediately realized something unusual was occurring. They had never observed a black hole or star in such a binary system. This discovery has led us to an altogether new astronomical concept we were unaware of. How did astronomers discover this? First, a black hole exists in that system. What makes the closest black hole we've discovered so special? Most significantly, what contribution has this discovery made to physics and astronomy? Regarding this discovery, astronomers utilize Gaia mission data. Gaia contributes silently to the field of astronomy. It is less prominent than the Hubble telescope or the James Webb Space Telescope. However, Gaia's extensive sky surveys have altered the trajectory of astronomy over the past few years, though only some are aware of this. It is a European Space Agency space observatory that was launched in 2013. Gaia constructs a three-dimensional map of the Milky Way using astronomy, which entails precisely determining the locations, speeds, and trajectories of stars and other astronomical objects to comprehend their origin and future in our galaxy. Gaia shares the L2 Lagrange point with the James Webb Telescope as it orbits the Sun 1 million miles from Earth. Since its inception, 3 datasets have been released by the observatory. The most recent one was in 2022. Gaia has revolutionized astronomy through these datasets, as many research papers are published daily based on them. For example, Gaia discovered a binary system comprising a solar-like star and a black hole in its third data transmission. Informal usage refers to the sources as Gaia BH1. The binary system is approximately 1,500 light-years away from Earth. It comprises a black hole with 10 times more massive stellar mass than the Sun and the G-type main sequence star with solar mass. Based on their surface temperatures, stars are classified into 7 primary spectral classes in stellar astrophysics: M, O, B, A, F, G, and K. The surface temperatures of O-type stars exceed 30,000 Kelvin, while those of M-type stars range between 2400 and 3700 Kelvin. This order can be remembered using a classic mnemonic: Oh, be a lovely woman, kiss me. According to this classification, a G-type star, like our Sun, would have a temperature between 5200 and 6000 Kelvin. Consequently, astronomers determined that the star in the Gaia BH1 system is a G-type star, with a surface temperature of approximately 5850 Kelvin, near the Sun's temperature of 5778 Kelvin. Because its mass is equivalent to the Sun's, the star is not identical like the Sun. Astronomers also found it peculiar that there was no significant mass transfer between the black hole and the G-star. Consequently, it is a dormant black hole that emits no X-ray radiation, making it even harder to detect. This brings us to the following inquiry. How did astronomers determine that the central object of the system is a black hole? It could be a dense neutron star or a white dwarf, which are challenging to detect because of their own luminosity. The answer resides in the star's orbit. Observing the star's motion in orbit because of a dark object's gravitational pull, astronomers deduce two intriguing facts about the binary system. First, the orbital configuration and orbital period. Consider this example from the research paper. The left quadrant depicts the predicted motion of the G-star in the sky over the next 6 years. After subtracting parallax and proper motion, the middle panel depicts the star's motion about its mass center, or barycenter. The final panel depicts the star's trajectory based solely on Gaia's astrometric solution. Its orbit around the unseen companion is mathematically elliptical and highly eccentric. Eccentricity gauges the deviation of an orbit from a perfect circle. Its value for the G-star is 0.45, twice that of Pluto's solar system orbit. The star's elliptical orbit revealed 185.6 days. Using these data, scientists calculated that the mass of the central dark object is roughly 10 times that of the Sun. The same calculation would hold true for two black holes with lesser masses, 5 neutron stars, 10 white dwarf stars, or 200 brown dwarfs at the center. The solution lies in dynamic stability. The presence of over two objects within the orbit of the G-star would render the system dynamically unstable. So it was determined that the unknown companion is a single stellar mass black hole or two compact objects, with black holes being the more likely possibility. The wobble is another intriguing aspect of the G-star's eccentric orbit. Only dark companions with the same mass as the bright object could generate such mass oscillation. Thus, the existence of a black hole was shown. However, this is where things become peculiar. The recently discovered binary system was atypical or unusual. Compare this graph between the black hole's mass and the star's orbital period within the system to known binary black hole systems. Gaia BH1 is distinguishable. Its characteristics resemble NGC 3201, a globular cluster with a distinct evolution channel, making their comparison irrelevant, and this is a major issue. Why? Because of its isolation from other binary systems, no stranded paradigm of binary evolution could adequately explain the origin and properties of this system. As with any significant scientific discovery, this raises some intriguing concerns. Astronomers have developed theories to explain the evolution of the system. The initial model is the stranded envelope evolution model. The mass of the black hole is 10 times that of the Sun. Therefore, its progenitor, the star that collapsed into this black hole, must have been larger than the current orbit of the star. This shows that the G-type star may have been engulfed in the progenitor's gas envelope, spiraled through it, and eventually expelled. This hypothesis sounds intriguing, but it is improbable that a star of solar mass could have discharged the gas envelope of a black hole progenitor with a high mass. Also, the extent of the star's orbit is much larger than the stranded envelope model predicted. Existing binary evolution models are also plagued by similar difficulties. The system may have formed dynamically in an open star cluster that disintegrated. However, the triple star system paradigm best explains the system's evolution. According to this hypothesis, the G-star was initially a tertiary companion to a close binary system composed of two massive stars. Their interaction prevented them from becoming red supergiants, eventually forming a two lower mass black hole binary system with a tertiary G-star companion orbiting in a slightly more compact orbit. If the system is a binary with a G-star and one black hole in the future, the G-star will become a red giant, resulting in the black hole accreting mass, and the system will become a binary system composed of a white dwarf and a black hole. However, suppose it is a triple object system composed of an inner binary of two black holes, and an external binary with a G-type star as the third component. In such a case, the merger of black holes may disrupt the evolution, causing the external binary to disintegrate. The discovery of the closest black hole with unique properties suggests our galaxy contains many binary systems containing quiescent black holes. Gaia's future data releases will facilitate the discovery of many additional quiescent black holes. An unknown universal force. The fifth fundamental force in nature, which physicists have sought for decades, may have just been discovered. However, how do we know that an additional force exists, and why is it necessary in physics? Everything visible in the universe is governed by four well-known fundamental forces. First is gravity, which causes the planets to orbit the sun. It governs the motion of celestial objects and is the weakest force in nature. Gravity governs everything, from colliding galaxies to merging black holes, to satellites, moons, and planets in orbit. The electromagnetic force that governs the motion of an electron around an atomic nucleus is the second force. In addition, the electromagnetic force is the force that controls the behavior of light. Light consists solely of an electromagnetic wave propagating through space. The weak nuclear force handles the radioactive decay of nuclei. The ultimate force is the strong nuclear force, which holds the protons and neutrons within the nucleus together. As its name suggests, it is nature's most powerful force. So far, so fine. To comprehend the origin of an additional force, we must return to the 1950s. The age of particle discoveries had arrived. Several novel particles are discovered each year. There was a quip among physicists that the Nobel Prize for the year must go to someone who did not discover any new particles. Experimentalists were ecstatic, but theoretical physicists were drowning in a sea of new particles, so they had to devise a plausible classification and explanation for the particles. Moreover, it predicts the existence of new species. Such a theory took more than a decade to develop. This theory is that standard paradigm for unifying three of the four fundamental forces in physics. Gravity is not involved. Einstein's general theory of relativity defines gravity more precisely. It is essential to comprehend the Standard Model to comprehend the so-called fifth fundamental force. The table of the Standard Model comprises four types of particles. The first family comprises 6 particles. Hadrons are composed of the fundamental particles protons and neutrons. Following are 6 leptons, electron, muon, tau, and the 3 neutrinos. The 4 gauge bosons, or force carriers, are the photon, gluon, W, and Z. The Higgs boson, the last missing element of the Standard Model discovered in the previous decade, has been discovered. Although a masterpiece is incomplete, the conventional paradigm of physics cannot reconcile gravity with other forces, and does not mention dark matter and dark energy, which account for approximately 96% of the observable universe. Therefore, physicists have spent decades searching for a new natural force. Analyzing the decay of the beauty quark makes it possible to locate this fundamental force in the quark family. An unstable particle decays into other particles in less than 1.5 quadrillionths of a second. Under the influence of the weak force, a quark decays into a collection of lesser particles, including electrons. An additional force of nature may manifest itself by subtly altering the rate at which quarks decay into other categories of particles. According to the Standard Model, a decaying quark should not be able to distinguish between an electron and a muon. A muon is identical to an electron except it is 200 times heavier. Therefore, the decay rate of the beauty quark into a muon must be identical to that of the electron. In March 2021, however, researchers determined muon decay occurred only 85% as frequently as electron decay. Nature favors one degradation pathway over another, a violation of the universality law of leptons. As exciting as it was to witness this anomaly, there was a 1 in 1,000 chance that the result was a statistical accident because of a random statistical fluctuation. Scientists refer to this value as 3 sigma. To be confident in a discovery or observation, we must achieve 5 sigma, which corresponds to less than a 1 in 1 million possibilities that the effect is because of a statistical fluke. Currently, researchers are analyzing additional LHCb experiment data. The B in LHCb represents attractiveness. However, attractiveness has yet to be studied by scientists, since all quarks are bound to form larger particles. Quarks decay directly. The March study examined the combination of beauty quarks and up quarks. The new findings investigated two decays, one in which the beauty quarks were paired with down quarks, and another in which they were paired with up quarks. It should not matter that the pairing is distinct because the decay occurring beneath the surface is identical. Scientists expect to observe the same effect if there is an unknown force, precisely what they observed this time. Muon decays occur approximately 70% as frequently as electron decays, but with a substantial error, so the result is approximately 2 sigma from the standard model. Approximately a 2% chance of being a statistical anomaly, but not precise enough to be conclusive evidence of an unknown force. This shows that the new study aligns precisely with the previous result and supports the notion that a significant breakthrough may occur. In the meantime, additional investigations at the LHC and the Bell, 2 Japanese investigations, are approaching the same measurements. Exciting because this research may shed light on the universe's most fundamental constituents. Dark energy enigmas. Dark energy could be produced by black holes. New research suggests that supermassive black holes may be the source of dark energy, one of the universe's most enigmatic entities. According to our most successful cosmological model, 68% of the universe comprises dark energy, while only 5% comprises conventional matter, such as stars and galaxies. Despite having similar names, dark energy and dark matter are distinct entities whose compositions remain a mystery to scientists. Comprehending whatever makes up dark energy is crucial because it determines the entire universe's fate. However, the problem is that, although it is an intriguing idea, only some people are receptive. How did astronomers conclude this? What observations of the universe led them to this conclusion? Most significantly, why is this concept so controversial? The first sign of the relationship between dark energy and black holes did not originate from either. Instead, it came from elliptical galaxies. These galaxies have an ellipsoidal shape and lack the spiral arms typical of their spiral counterparts. Their star populations are typically older and redder. Elliptical galaxies are believed to be in the final phases of galaxy evolution. Future collisions and mergers of spiral galaxies or the gravitational collapse of interstellar gas clouds will probably produce them. For example, it is hypothesized that when the Milky Way collides with the Andromeda Galaxy, its spiral structures will transform into an elliptical galaxy. Despite their diverse origins, all elliptical galaxies observed lack the gas and dust required for conventional star formation. This deficiency is attributed to a supermassive black hole at the galaxy's center, which accretes mass from the surrounding stars, limiting their development and eventually depleting the fuel required for star formation. Consequently, the black hole ceases to accrete, resulting in a galaxy devoid of new stars. This relationship between supermassive black holes and the termination of star formation in elliptical galaxies is essential for comprehending the relationship between black holes and dark energy. Once formed, elliptical galaxies are stable in mass and shape. However, recent research shows that the mass of some elliptical galaxies increases over time, prompting astrophysicist Duncan Farah and his colleagues to investigate the evolution of these galaxies in greater detail. Their research focused on elliptical galaxies of varying ages whose nuclei contained millions or billions of times more massive supermassive black holes than the Sun. When drawing galaxy maps, the team observed a perplexing trend about their black hole and stellar mass in this graph. The crimson dots represent old ellipticals in the vicinity. Blue dots represent ellipticals from 6 billion years ago, while orange dots represent ellipticals from the first 2 to 3 billion years of existence. Astronomers have compared the same juvenile elliptical galaxies that emerged in the early universe to the old elliptical galaxies we observe in our local universe. By comparing them, astronomers can study the transformation of juvenile galaxies into the galaxies we observe today. However, the correlation between the mass of the stars in the galaxy and the mass of the supermassive black hole was significantly off. Black holes at the nuclei of low redshift elliptical galaxies had masses 7 to 20 times greater than predicted by research on galaxies with high redshift. This unanticipated discovery challenges our current understanding of the evolution of galaxies. Where is the extra mass coming from if ellipticals are stable once entirely formed? This query may be answered by dark energy. However, to comprehend how dark energy may be related to the excess mass of black holes in elliptical galaxies, it's necessary to investigate two essential concepts: vacuum energy and cosmological coupling. The energy that pervades all of space and time is called vacuum energy. This energy results from the constant emergence of virtual particles within the constraints of the energy-time uncertainty principle. The total energy of vacuum fluctuations is relatively constant despite the apparent randomness of this process. The interior space, or vacuum, also expands as the universe expands, increasing the total vacuum energy. The new model suggests black holes have an expanding energy deficit within their interiors. Consequently, the black hole's energy increases. According to Einstein's mass-energy equivalence, the black hole's mass must increase as energy increases. However, the black hole exerts negative pressure outward to conserve the universe's energy. This negative pressure speeds up the universe's expansion by pushing everything around the black hole away from it. The precise nature of dark energy is the negative pressure exerted by the black hole. According to the equation of state, the energy density of dark energy is equivalent to the negative pressure it exerts. This implies that dark energy and black holes are cosmologically coupled or interconnected. A straightforward equation can describe the cosmological coupling. Here, m is the mass of the black hole, and a is the scale factor that characterizes the universe's expansion. So I is the initial universe scale factor when coupling begins, and m of I is the initial black hole mass. As the universe expands to a scale factor of a, its mass will transform to m of a, so k represents the dependence of the ultimate mass on the universe's expansion. The term for this is cosmological coupling strength. According to their hypothesis, if there is no cosmological coupling in the universe, k is 0, and the initial and final masses of a black hole are the same as the universe develops, then there is no cosmological coupling. However, if cosmological coupling exists, k should equal 3, so the black hole's mass after the universe's expansion is greater than its initial mass. This is the essence of the intriguing concept underlying their investigation. The possibility that black holes could be a source of dark energy is intriguing, but is there any evidence to support this theory? How could they corroborate this theory when the interior of a black hole is unknown? To answer this question, researchers turned to low redshift elliptical galaxies where they had previously observed an increase in the mass of the supermassive black hole. Using the cosmological coupling equation, which defines the relationship between the expansion rate of the universe and the vacuum energy density, they compared the masses of these black holes with those of young elliptical galaxies. K, representing the coupling parameter, was unexpectedly determined to be 3.11. The probability of these galaxies having a K value of 0 was close to 0, showing that the black holes in these galaxies are cosmologically coupled with the universe. Additional analysis revealed that black holes could account for approximately 68% of the universe's total dark energy. This result also explains the coincidence problem, which asks why dark energy has lately dominated the universe. This study suggests that a complete evolution of galaxies is required for black holes to contribute to and dominate dark energy, speeding up the universe's expansion. As exciting as the proposed concept may sound, it must be acknowledged that it has some limitations. These result from several gaps in the hypothesis. First, because of the impossibility of studying a single galaxy throughout its existence, the researchers compared galaxies from different periods of the universe. However, this comparison implies that galaxies' evolution and growth paths were similar across eras, which may be different. Second, they assume black holes exert negative pressure, a property of dark energy. Third, the study only considers singularity-free black holes, which are not well established in the scientific literature. However, we cannot outright reject theoretical concepts such as this one. Some of the most revolutionary discoveries in physics and astronomy began as theoretical hypotheses. For example, the 1930 prediction of neutrinos by Wolfgang Pauli led to their discovery in 1956. Similarly, the discoveries of Neptune, the Higgs boson, and gravitational waves were based on theoretical predictions. Therefore, we must remain speculative and seek evidence to determine whether the concept is merely a mathematical beauty or if it represents physical reality. The Little Galaxy's Enigma. The mystery of dark matter is one of cosmology and astrophysics' most intriguing unresolved problems. According to astronomers, approximately 1/4 of the observable universe comprises of dark matter. According to estimates, 85% of the matter in galaxies comprises dark matter. According to our current models, the fundamental components of cosmological structures are dark matter halos. Consequently, they play an important role in the formation and evolution of galaxies, shielding them from the gravitational influence of their companions. With them, galaxy formation is possible. However, astronomers have discovered something peculiar in a galaxy cluster 62 million light-years away. Recent research on dark matter may pave the way for an entirely new branch of physics. So what makes the galaxies in this distant cluster so special? What challenges do these galaxies pose to our current cosmological models? How, most critically, will this discovery affect the future of cosmology and astrophysics? Dark matter is a hypothetical matter thought to exist nearly everywhere in the observable universe. Dark matter, unlike normal matter, does not interact with electromagnetic forces. As a result, it cannot absorb, reflect, or emit light, making it exceedingly difficult to detect. Therefore, it has been given the name dark. However, astronomers have presumed its existence because the star's motion and galaxy's dynamics would make no sense without it. Furthermore, according to various theories, the preponderance of dark matter is non-baryonic. This implies that the standard model of physics does not include subatomic particles. Instead, these enigmatic particles can interact with massive particles weakly or gravitationally. Dim brown dwarfs, white dwarfs, and neutron stars are additional likely candidates, although even the most sensitive detectors could not discover conclusive proof of the existence of dark matter. The gravitational influence of dark matter on the surrounding visible matter shows that something mysterious, such as dark matter, exists. The issue is caused by dark matter halos. A dark matter halo comprises gravitationally bound masses of dark matter. Consequently, they impose a strong gravitational pull on nearby galaxies. However, if we cannot observe these halos, how do we know that they interact with galaxies? To comprehend this, let's contemplate a simple illustration. When an object exerts its gravitational force differentially on various parts of another body, it can distort that body's natural shape, causing tides. Because of the moon's gravitational pull, it's analogous to Earth's tides. As a result, the moon exerts a greater force on the side of the Earth, confronting it. It is believed that the universe contains trillions of dwarf galaxies. They are the most common and tiniest galaxies in the universe. Dwarf galaxies are typically found in massive galaxy clusters, or close to much larger counterparts. This renders these small galaxies susceptible to gravitational distortions induced by their enormous companions. However, their dark matter halos save the day. They partially shield the dwarfs from the massive cluster's tides, limiting their distortion. All galaxies are believed to reside at the center of a vast sphere of dark matter, which dwarf galaxies containing even higher proportions of dark matter than large spirals. This is because the sum of their stellar masses cannot completely explain the motions of their stars. An example is Tucana II, a dwarf galaxy of ancient stars near the Milky Way. It is devoid of ongoing star formation and has abundant dark matter. Halo, however, the Fornax cluster, located 62 million light-years away, is an exception. According to the standard model of cosmology, it comprises several warped and perturbed dwarf galaxies. If these dwarfs are surrounded by halos of dark matter, such distortions should not exist. The researchers analyzed the Fornax Deep Survey (FDS) data in their article. It contains information on 564 galaxies and is the most recent survey of the Fornax cluster. First, the researchers eliminated the galaxies they believed did not belong to the cluster and represented line-of-sight contamination instead. Additionally, they eliminated galaxies with ambiguous tidal morphology to improve the analysis. From the Fornax survey, they were left with 353 dwarf galaxies. to gain a comprehensive understanding of the peculiar characteristics of Fornax dwarfs. Researchers attempted to comprehend the gravitational distortions of these galaxies and their causes. Each galaxy's distortion is determined by several factors, including its intrinsic properties and distance from the cluster's core, where gravitational forces are significantly stronger. Therefore, galaxies with large sizes but few stars, and those closer to the cluster's core, are readily perturbed. Researchers contrasted their cluster observations with the European Southern Observatory's VLT survey telescope, and their findings show some issues with the standard model. According to the conventional model, the dark matter halos of these dwarfs should partially protect them from the cluster's tides. In contrast, they are distorted and entirely unprotected. The galaxies in the paper were categorized as undisturbed, mildly perturbed, severely disturbed, and unclear. In addition, the researchers provided images of 3 survey dwarfs displaying varying disturbance levels in various color bands and filters. This picture depicts an undisturbed galaxy. This galaxy exhibits signs of tidal distortions, which places it in the category of being mildly perturbed. This is the image of one galaxy in the category of being extremely perturbed. Because of the gravitational influence of neighboring galaxies, traces of tidal perturbations can be observed. Suppose that the standard model must explain the observations. In that case, the Fornax dwarfs ought to have been annihilated by the gravity of the cluster core, even when their tides are 64 times weaker than their gravity. This contradicts previous studies in which it was found that the force required to disturb a diminutive is greater than previously estimated. The galaxy is roughly equivalent to its own gravitation. If the astronomers' findings are confirmed, then the standard model of cosmology requires significant revisions. Do we have any other explanation for the peculiar behavior of the Fornax dwarf galaxies? At least one alternative explanation exists for the peculiar galaxy morphologies predicted by the changed Newtonian dynamics model, also known as the Mond model. To account for the observed properties of galaxies, this model suggests that Newton's law of universal gravitation should be changed. Then it could explain the bizarre galactic appearances. In 1983, Israeli physicist Mordecai Milgram first proposed the concept of Mond. The original purpose of the hypothesis was to explain why observed star and galaxy velocities were greater than predicted by Newtonian mechanics. Therefore, it is an alternative to the dark matter hypothesis for explaining why galaxies appear to violate currently understood physical laws. While Mond is an ideal alternative to the lambda CDM model for describing the dynamics of spiral galaxies, it could be faultless. For instance, Mond cannot describe galaxy cluster masses by a factor of 2 to 3. In addition, it cannot account for the observations of the Bullet cluster located 3.7 billion light-years away. It will be fascinating to see which of these two models ultimately prevails. If scientists continue to discover more galaxies devoid of dark matter halos, we may need to reevaluate our current standard model of cosmology. According to our galaxy evolution models, even the James Webb Space Telescope has discovered candidates that should not exist for galaxies. This is an exciting period for astronomy. One of them is the candidate for Schrödinger's galaxy, which we discussed in the 20th episode of the series when Webb was operating at full capacity. Astronomers hope to discover dozens of candidates with a high redshift and thoroughly study their composition. Pole shift is happening. The Earth's magnetic field is one of its most important protective barriers. This invisible structure surrounding and penetrating our blue home planet protects it from the solar wind's charged particles. If the Earth's magnetic field did not exist, terrestrial life would not have developed to its current state. Would the magnetic shield be affected if the Earth's magnetic field changed significantly? Several such pole climbs have already occurred in the past. Our planet's magnetic poles are reversing. But how would this impact everyone? What else? Consequently, a procedure may have been started. Today's aim is to discover answers. On Earth, a magnetic field exists. According to various hypotheses, magnetic fields are generated by diverse methods. However, the dynamo theory is the most widely acknowledged. Likewise, it is believed that the geodynamo is the mechanism responsible for the Earth's magnetic field, based on the premise that the interior of the Earth contains vast quantities of electrically conducting liquid. This theory proposes that the outer liquid portion of the Earth's core completely encircles the solid center and contains a very high iron content, almost entirely composed of pure iron. It is estimated that the innermost regions of our planet have temperatures exceeding 9,000 degrees Fahrenheit. This value corresponds to the Sun's surface, nickel and iron's searing heat. Under the pressure and temperature conditions that exist in the Earth's interior, however, it cannot be magnetized. Therefore, they are solely conductors of electricity. In addition, the dynamo theory proposes that connections in the Earth's interior move matter. These currents transport molten material from the planet's interior to the cooler outer regions. After the material has cooled, it descends back into warmer regions. The Coriolis force influences the convection currents within the interior of the planet. Because of the planet's rotation, currents are deflected and directed along helical paths. According to dynamo theory, this helical motion sustains the present generation. Consequently, the initial, fragile magnetic field gained increasing strength. The magnetic field eventually became relatively stable when a limiting effect occurred. A defensive shield and a marker, the Earth's magnetic field protects us from the solar wind. This accounts for approximately 95% of our natural defenses. Electric currents in the ionosphere and magnetosphere contribute to the remaining components. A spatially variable interference field completes the magnetic field of the Earth. This procedure results in the appearance of breathtaking auroras. When charged, energetic particles interact with the Earth's magnetic field. Dazzling luminous phenomena occur. In addition, our invisible companion performs several other crucial functions. Consistent with its name, some animals, including pollinators, sharks, salmon, and migratory birds, possess magnetic senses. Because of the Earth's magnetic field, these organisms can navigate without error. Humans have used and continue to use the Earth's magnetic field for purposes other than navigation. The Earth's magnetic field is also suspected of directly influencing global temperature variations. Some experts are skeptical that manufactured climate change explains the accelerated warming of our planet. Consider a classic compass for a moment. In some experiments, cosmic rays have been attributed to cloud formation. In a biased poll, however, many researchers believe this link is insufficient to substantially affect global climate change. Upon examining the history of the Earth's magnetic field, we realize it is not a rigid, immutable entity, but a construct that undergoes dynamic change during its examination. The polarity of the Earth's magnetic field has reversed over thousands of years. How can these changes, sometimes traced back hundreds of thousands of years, be demonstrated? Magnetic fields cause magnetic minerals that are cooling to become magnetized. Scientists use the magnetization traces left in rocks when the temperature declines below the Curie temperature. Furthermore, detritus can be magnetized. However, ceramics are no different. Because of the magnetization of the oceanic crust, the principal magnetic field of the Earth remains essentially stable over extended periods, but its intensity fluctuates slightly. Therefore, the associated materials genuinely understand the natural processes that once occurred on our blue home planet. For this reason, their value in geology and archaeology is immeasurable. A pole leap in the Earth's magnetic field is also relatively common. Approximately every 250,000 years, the polar regions reverse positions. About 780,000 years have passed since the last pole leap, and this procedure is referred to by experts as the Bruns-Matsuyama reversal. The pole leap required less than 100 years. Unlike complete magnetic field reversals, temporary dips occur when the field regains its original direction. Unexpected developments. The magnetic poles could slowly adjust, but what would happen to them? They are already doing it because of the daily north-northwestward movement of the Arctic magnetic pole. The magnetic pole, therefore, moves approximately 19 miles per year. Besides its direction, the Earth's magnetic field can also be measured by its speed and intensity. These fundamental attributes are subject to continuous change. Gauss was the first person in the first half of the 19th century to measure the Earth's magnetic field. In 1839, the Magnetic Association concluded that the central position of the Earth's magnetic field derives from the planet's interior. Since our magnetic field was first measured a century ago, its intensity has decreased by nearly 10%. The intensity of the terrestrial magnetic field decreased by 6%. Observations by the swarm satellites show that the magnetic field intensity of the South Atlantic is diminishing. However, it is gathering strength in the Indian Ocean. Is there a rationale for this change's rapid occurrence? This interesting question still needs to be satisfactorily answered by science. The cosmological field intensity is decreasing. However, it is gathering strength in the Indian Ocean. Is there a rationale for this change's rapid occurrence? This intriguing query has yet to be satisfactorily answered by science. The magnetic field in the core is already altering its regional polarity and producing a forgery. Therefore, the global field could degenerate much more rapidly than would be permitted by passive decay. However, even if the dynamo failed, the magnetic field would still take 10,000 years to decay. Therefore, it is necessary to review two truths. First, statistics show that the polarity of the Earth's magnetic field reverses every 250,000 years. However, 780,000 years have transpired since the previous pole jump. The time for a new pole reversal has arrived. How would our lives change if the magnetic poles were tilted in this direction? The computer models of experts portray a stunning picture. Initially, there would be 4, 8, or more magnetic polarities. There would be no magnetic field on Earth in the traditional sense. As a result, our planet's protective shield becomes disorderly and chaotic. However, such events will not eradicate the invisible construct entirely. In the past, 10% of its current intensity existed. Therefore, terrestrial life is unlikely to sustain enduring damage. In such a scenario, Earth would be bombarded with more cosmic particles. Additionally, this would increase the prevalence of genetic disorders and malignancies. However, the Earth's magnetic field's polarity has never been explicitly linked to mass extinction. Homo erectus, our remote ancestor, survived the Bruins-Matsuyama reversal 780,000 years ago. How about the creatures that navigate using the Earth's magnetic field? According to several researchers, migratory birds and similar species are exceptionally adaptable. These animals realign their magnetic sense nearly every day. The animals oriented themselves primarily towards the sun at night, but their sense of smell, ocean currents, and geographical landmarks prevented them from becoming disoriented. In contrast, our technical systems are more susceptible to attack. For instance, passaging charged particles can occasionally completely obliterate electronic components. Specifically, the internet, television, telephone, and GPS navigation satellites would be affected. In addition, some scientists assert that severe magnetic disturbances could paralyze the U.S. power grid. As a result, such an occurrence would have many negative repercussions, such as a breakdown of water supplies, food processing, products, transportation, and the internet. Does this imply that the magnetic field of the Earth has already reversed? We must determine the answer to this query. The potency of our natural shield will be determined. The Parker Solar Probe departed our Azure home planet on August 12, 2018. Since then, NASA's spacecraft has conducted extensive research on the Sun. The outer atmosphere of our parent star, the corona, will be primarily focused on the mission of the uncrewed spacecraft. Io, the Moon. Io is one of the many peculiar objects in our solar system. The innermost of Jupiter's large moons is distinguished by volcanoes, the aurora, and sulfurous atmospheres. It has a specific context, so let's learn more about it. We currently know that Jupiter has 79 moons. A few orbits in and around the planet's rings are near the planet. In 1610, Galileo also discovered 4 massive moons, which he dubbed the Galilean moons. Io, Europa, Ganymede, and Callisto are listed from innermost to outermost. There are also irregular moons of Jupiter that are significantly more distant than the preceding moons. Io is only 350,000 kilometers from Jupiter's cloud peaks. From the surface of Jupiter, it would appear 39 times more conspicuous in the sky than our moon. Io orbits Jupiter in 42.5 hours, whereas our moon takes 30 days. The orbits of 2 of the Galilean moons align with their own. Europa orbits twice for every orbit of Europa, while Ganymede orbits 4 times for every orbit of Europa. This is known as orbital resonance. Orbital resonances increase the mutual gravitational influence between the moons, causing Io's orbit to be slightly more eccentric than without them. In its orbit, Jupiter's gravitational influence causes tidal heating, the primary heat source for most of its geological activity. On Io, tide bulges can reach 100 meters in height. Similarly, the Moon causes ocean tides on Earth. Typically, Earth's tides are only 2 meters high or low, which is a much smaller effect. Because of its proximity to the massive planet in our solar system, I always experience 300% greater tides than our Moon. Jupiter and the other large moons in the system prevent the Moon's orbit from becoming less eccentric, so Io won't be able to relax for a while. In Io, a day corresponds to its orbital rotation. Therefore, it is tidally bound to Jupiter. Just as we can only observe one moon phase from Earth, from Jupiter, there is only one perspective of Io, despite its bulk. This Galilean moon is relatively large. Comparable to the terrestrial planets, our moon, due to its size and density being comparable to the moon, its gravity is also comparable. It has the greatest density of any moon in the solar system, which is an intriguing fact. This is one of its many distinctive features. In addition, it consists primarily of silicate, granite, and iron. Io is the smallest liquid entity in the solar system. Most of the solar system's other large moons are composed of water, ice, and silicates. An iron or iron sulfide core will likely surround a silicate-rich mantle and crust. Since no magnetosphere surrounds the moon, the core cannot be convective. A liquid mantle near the crust has a minimum thickness of 50 kilometers. Its surface is covered by a multitude of enormous volcanoes. Here is the origin of all volcanism. This is where Io excels. Before the 1970s, we knew little about the Internet of Things, Io. While observatories indicated the moon lacked water and could be covered with sulfur. Pioneer 11 was the first mission to investigate Io in depth, even though the quality required refinement. However, Io is composed of silicate rock instead of water ice, and its atmosphere is sparse. Because Jupiter's radiation interfered with the onboard command system of Pioneer 10, close-up images of Io were not captured. Due to Pioneer 10's exposure to radiation, the maximum radiation around the planet was 10,000 times stronger than what Pioneer 10 experienced. In 1979, the initial and second Voyager missions to Jupiter were launched, with only 20,000 kilometers separating them. Voyager 1 captured close-up images of Io's surface. The landscape was completely devoid of impact craters and was filled with vibrant colors. We have mountains taller than Mount Everest and volcanic craters hundreds of kilometers across. There were also visible lava flows. However, it was notable that vapors were rising from the surface. There is no other location like Io, proving its volcanic activity. Beyond Earth, the phenomenon has been observed excluding cryovolcanoes. The study discovered that sulfur compounds dominate the atmosphere. Moreover, Voyager 1 confirmed that Io's surface is covered in sulfur thrusts. This is the reason Io is so vibrant. In March of 1979, Voyager 1 observed 7 of the 9 plumes, while Voyager 482 observed 7 from 1 million kilometers away. Therefore, it is probable that these volcanoes were active throughout those 4 months. The Galileo spacecraft arrived on Jupiter in 1995 and captured captivating images. Even though the spacecraft was not intended to investigate Io, it captured some of its best images to date. Because of mechanical malfunctions, Galileo could not operate at full capacity, meaning we would have obtained even better images if it had been entirely functional. However, volcanic emissions were observed. Volcanic eruptions were also confirmed. Magmas that contain sulfur and silicate similar to Earth's magma. Io's magma is also magnesium-rich. Io's surface contains an astonishing quantity of color. Yellow plains are predominantly composed of sulfur. Fresh sulfur dioxide frosts cover the vast majority of the polar regions. Because of radiation damage, the polar regions are more crimson than the rest of the planet. Red deposits left by volcanic emissions that reached hundreds of kilometers above Io can also be observed in other locations. Peel, a dormant volcano, has the most noticeable deposit. Galileo was also present. When Voyager passed, an enormous plume was visible. The plume is 300 kilometers in height and 1,200 kilometers in breadth, approximately the extent of Alaska. Intriguingly, lava flows typically originate in depressions at the summits of volcanoes. On Io, there are no depressions on lofty peaks. As a result, there are these lava lakes surrounded by tall walls. Loki, one of the most prominent volcanic depressions on Io, is displayed here. The circle's diameter is 200 kilometers. The legs are directly connected to the magma reservoir below, typically covered with a thin crust layer. Loki generates 25% of the average heat output of Io, but when the crust on the lava lake descends back into the lake, Loki's heat output increases by a factor of 10. A second massive volcano on Io shows this exceptionally well. Vashti is included as well. This area is typically white, but only white in this image because of the crust collapsing. Because of this intense radiant energy emitted by the magma curtain, the camera captured only white images. In 2007, Jupiter provided new horizons with a gravity assist on its journey to Pluto. Besides testing its apparatus, the company seized the opportunity. Vesta's lens focused on Io as it flew by, revealing details unique to Vesta. A cloud could be seen hundreds of kilometers above the surface of Io, emanating from the volcano I mentioned. Also visible around the moon are additional minor eruptions. This is the most remarkable spacecraft I've ever seen. Volcanoes are typically flat, but the highest mountain is 18 kilometers tall. Occasionally, mountain ranges and ridges connect these mountains, although the majority are not volcanoes. Lava lakes surround these mountains, signifying faults in the crust. Jupiter's magnetic field is another distinctive feature of Io. Jupiter has a vast and potent magnetic field, and Io orbits within some of its most significant sections. Particles are lost to space from Io's thin atmosphere, and emissions float in a natural cloud surrounding Jupiter. This cloud can stretch for many miles beyond and behind Io's orbit. Similarly, Jupiter's magnetic field generates a plasma torus, a donut of ionized particles. Io's orbit rotates at 17 kilometers per second, whereas Taurus's is at 70 kilometers per second. As a result, Taurus-originated particles bombard the neutral cloud during Io's orbit, causing it to gain energy. Attracted by the magnetosphere's magnetic field lines, these newly ionized particles enter Taurus. Approximately 1 ton of matter is lost from the neutral cloud each second into the Taurus plasma, substantially increasing Jupiter's magnetic field. If Jupiter's magnetosphere were visible, it would have a dimension comparable to the Moon's. However, there is more to the relationship between Io and Jupiter than meets the eye. The Io flux conduit is an electric current that connects Io's atmosphere and neutral cloud to Jupiter's polar upper atmosphere via the magnetic field lines that Io traverses. Flux tubes are essentially magnetic field line concentrations. These are visible on the Sun between sunspots because of the charged plasma that flows between sunspots. Io's flux conduit generates an aurora around Jupiter's polar regions. The flux conduit of Io collides with Jupiter's upper atmosphere. Aurora can also be seen on EIR. The colors that depict ionized particles are not limited to the polar regions. Sodium is green. The red hue is derived from oxygen, while the blue hue is derived from sulfur. Here you will find all of the information you need about Io. Pluto. Pluto has always been a source of controversy in astronomy. Does it make up a planet? Because of its great distance from Earth, Pluto was shrouded in mystery, and we knew little about its appearance. However, traveling through space took 9 years. The New Horizons mission of NASA was the first to reach Pluto. Stunning images of Pluto and its surrounding Kuiper belt have irrevocably altered our perception of the planet. Pluto and its extraordinary satellites, a magnificent universe before the invention of modern observatories, Pluto was considered the 9th and most distant planet from the Sun. Then, in 1905, an American astronomer named Percival Lowell discovered Pluto's existence by observing some peculiar deviations in the orbits of Neptune and Uranus, Pluto's nearest neighbors. According to him, the two planets may be pulled apart by the gravity of another world. Unfortunately, he passed away before its discovery in 1915, so he could not witness it. Clyde Tombaugh discovered the planet in 1930 at the Lowell Observatory in Flagstaff, Arizona, following the predictions of Lowell and other astronomers. Pluto's name also includes the initials of Percival Lowell as a tribute to him. Following the suggestion of 11-year-old Venetia Burney of Oxford, England, the Roman deity of the underworld was given this name. Scientists and astronomers have attempted unsuccessfully for years to glimpse the planet. Following the discovery of Pluto, there were many hypotheses and predictions, but no supporting data or images. The new world was too distant for precise observation, so NASA launched a mission to get up close and personal. The $700 million mission, to be exact. On January 19, 2006, Cape Canaveral launched the New Horizons mission to investigate the neighboring planets. Jupiter and Saturn were the primary targets for the New Horizons spacecraft, but Pluto was the ultimate aim. Despite the many obstacles encountered along the way, the journey required effort. New Horizons effectively explored Jupiter and its Jovian moons, returning many heavenly images and data that improved our understanding of the giant planet. The New Horizons mission gathered crucial data after its close encounters with Jupiter, Io, Europa, and Ganymede. After several course corrections and periods of hibernation, New Horizons was directed towards the Kuiper Belt. The spacecraft required 9 years to reach its destination. On July 14, 2015, the New Horizons mission officially reached Pluto. It did a fast flyby of the planet, but could collect 6.45 gigabytes of data. Particle and dust detectors downloading the data may have taken a few minutes in the past, but it may take more than a few minutes today. Data transmission in space is distinct from data transfer on Earth because of the distance of 2.9 billion miles between the spacecraft and Earth. It took 16 months for the data to reach Earth. Throughout the spacecraft's exploration of the Kuiper Belt, the third region of the solar system, it continued to move away from the planet. Here, Pluto once resided. This is where they made the discovery. Pluto was discovered to be a massive Kuiper Belt object, or KBO, rather than one of our 9 planets. This enigmatic belt extends from 20 AU to 50 AU, circumnavigating the solar system. 1 AU is the distance between Earth and the Sun. Pluto is one of the largest ice objects in the Kuiper Belt. According to mission data, approximately 35,000 space objects are present in the region. This is not an ordinary space asteroid. It is the remnant of the solar system. By examining the formation of these ice rocks, we could gain a greater understanding of the solar system. New Horizons mission transmitted information about the belt. In the past, we'd only observed comets as floating icy bodies. Typically, comets are observed after the sun has warmed and transformed them. Despite Pluto's location at the border of the solar system, suspended in the Kuiper Belt, the mission allowed us to observe these objects in their natural environment. When Pluto was exposed to the cold, it was a busy and scientifically significant world. During its flybys of the planet, New Horizons captured every angle and image conceivable. Consequently, it was revealed that the planet possessed some remarkable characteristics. New horizons were observed, and high-resolution images were obtained during Pluto's flyby. The dwarf planet reoriented itself to face its moon because of the Sputnik Planitia region on its left. The mission transmitted images of a heart. The Tombach region is a vast, 1 million square mile, heart-shaped nitrogen glacier. Charon, the largest glacier in the solar system, extends across the left lobe of Tombach for approximately 600 miles. Images and data show that the ice flow is largely crater-free and exceptionally juvenile. The detection of water ice on a distant planet was one of the mission's most exciting discoveries. Since water ice is limited, discovering additional water ice beneath the surface excited researchers. Existence is possible wherever there is water. There were also photographs of mountains as lofty as the Rockies. Because of this, and the absence of craters, the planet is geologically active. Other surprising Pluto features include dunes. The sand dunes on Earth are not identical to these. Granules of solid methane ice sculpt Pluto's dunes. It is essential to observe that dunes are uncommon in our solar system. They're found only on Earth, Mars, Venus, Saturn's moon Titan, and Comet 67P. LORI, the spacecraft's long-range reconnaissance imager, also captured a brilliant blue image of Pluto. The blue hue is produced by dispersing sunlight with hydrocarbon particles called tholins in the planet's atmosphere. You would be utterly mistaken if you believed the dwarf lived in a miserable, frigid world. In addition, the New Horizons mission revealed that Pluto is much more significant than previously believed. With a diameter of 1,473 miles, it can, once again, be considered a planet. In addition, the spacecraft gained stunning images of Pluto's moons. Charon, Pluto's moon, is a wild, wild realm. According to mission data, a liquid ocean may exist beneath the frozen crust of Chiron. In contrast, two other satellites in the solar system, Styx, Nix, Kerberos, and Hydra, rotated quickly while maintaining a face towards Pluto. Finally, a successful flyby of Pluto led New Horizons to encounter the mysterious Kuiper Belt object Erica Earth. This strange, lobe-shaped object is the consequence of combining two objects. Undoubtedly, it is the most primitive binary we have ever investigated. The images captured upon approach revealed its uncanny resemblance to an icy snowman. Nearly 4 billion miles from Earth, this object in the Kuiper Belt may contain crucial information about other primordial Kuiper Belt objects. According to the International Astronomical Union, the object's distinguishing characteristics are named after air, which signifies the sky, and Powhatan Algonquin. The team researching Kuiper Belt objects will assign names to Air Core's most prominent features in 2019. The close-up image of the object reveals a nearly circular trajectory on the larger air lobe and a larger crater. Three characteristics receive unfamiliar names in the reduced first, as is, because it resembles a serpent. The arc will be named after the Mayan language of Yucatan. In Bengali, it is known as Quasar, which means sky. In English, the enormous crater is known as the sky. After New Horizons flyby, a few aircraft images were captured as it explored other objects in the belt. If another spacecraft cannot make the journey, we will never see Pluto or Earth again. Humanity has been compelled throughout history to seek the unknown and explore the world beyond. The Voyager spacecraft has shown that this force has no limits. We have already reached interstellar space thanks to two legendary sister spacecraft. No manufactured spacecraft, regardless of how impressive, can last forever. The New Horizons mission is expected to continue for another 16.5 years, traveling 311 million miles, or 500 million kilometers, per year, the distance between Earth and Jupiter. The crew suggests that one more space region can be investigated before time runs out. As with the Voyager probes, many scientists believe New Horizons may travel much further than expected. New Horizons are currently thriving and show no signs of slowing down. How will its future unfold? Time alone will provide the answer. There is still much to learn about Pluto and its satellites. Some consider it to be a dwarf planet in the Kuiper Belt. Pluto reigns supreme among the planets.